Hello everyone, this is lecture 27 of the subject analog circuits. In this class, I am going to discuss precision rectifier and Schmitt trigger. So, in last two classes, I had discussed about the basics of operational amplifier, what are the different configurations in which we can use operational amplifier and what are the applications of those configurations. So, we had seen in last two classes that in operational amplifier we can use it in two modes, either in open loop mode or in closed loop mode. In open loop mode there is no feedback path, but in closed loop mode there is a feedback path. That feedback path, it may be negative feedback, it may be positive feedback. Negative feedback means your output is connected to the negative input terminal of the op amp. Positive feedback means output is connected to the positive input terminal of the op amp. And we had seen that in open loop configuration of op amp there are very limited applications, especially that application is voltage comparator. When we want to compare two voltages and accordingly the output voltage is generated, for that there is a voltage comparator circuit. In voltage comparator we use the open loop configuration of op amp, but in closed loop configuration of op amp there are different applications. We had seen few of them, like if there is a resistor at the inverting input terminal and there is a capacitor in the feedback path, in the negative feedback path, then it becomes integrator. If we interchange this resistor and capacitor, then it becomes differentiator, right. Similarly, there are other applications like log, anti-log amplifiers, etc. So, these are the applications of operational amplifier. Now, we are going to see another application of operational amplifier, that is the precision rectifier and Schmitt trigger. So, firstly I am going to start with the precision rectifier. So, first of all we need to understand that what is the difference between the normal rectifier, which you know, and this precision rectifier. So, the rectifier is a circuitry which converts AC into DC, alternating current into direct current. So, the normal rectifier which we had already studied earlier, that normal rectifier is used in power supply, but the issue with that particular normal rectifier is that whenever the input signal magnitude it is very small, then there will be issue. What can be the issue? Since we know that in normal rectifier we are using diodes, silicon diodes, and the voltage drop across the silicon diode, that cut in voltage, that is approximately 0.7 volt. But if the input signal magnitude it is very less, for example 0.1 volt, 0.2 volt, then that normal rectifier will not work, because for the diode to be on, that voltage drop across the diode, it should be 0.7 volt. It means that if the magnitude of the input signal it is 0.7 volt or above, then that normal rectifier is fine, but if the magnitude of the input signal is very small, it is in the range of, if it is in the range of 0.1 volt, 0.2 volt or even smaller, then that normal rectifier will fail. That is your conventional amplifier. That is the main limitation of the conventional rectifier, that is it cannot be used when the input signal is very small. Now, this small input signal, it is being generated especially in instrumentation systems. In instrumentation systems, the signals which are generated from the sensors, it is of very small magnitude. So, in instrumentation system we cannot use this conventional rectifier. So, the need of a rectifier arises which can be used even for a very small magnitude of signal in instrumentation systems. That rectifier is precision rectifier. Now, how this precision rectifier, it removes the drawback of the conventional rectifier. This precision rectifier, it is used in instrumentation systems, it is used where the input signal magnitude is very small. Now, how this precision rectifier works? In precision rectifier, along with diode we use op amp, but in normal rectifier, in conventional rectifier we do not use this op amp, we only use diodes. Like in half wave rectifier we use one diode, in full wave bridge rectifier 4 diodes are required, but there is no op amp there. But in precision rectifier, along with diode, operational amplifier is used, and the combination of this diode and op amp is called super diode. So, super diode, it is the combination of op amp plus diode, and the reason why this precision rectifier, it can be used for a very small magnitude signal, the reason is that the gain of the operational amplifier is very high, that we had seen in the op amp basics. Ideally the open loop gain of the operational amplifier, it is infinite, but practically for 741 IC the gain is around 10 to the power 5 to 10 to the power 6, that gain is very high. Since the gain of the op amp is very high, so it can process the very small magnitude signal that is generated in the instrumentation system. That is the reason why this precision rectifier is especially used in instrumentation systems. The reason is because of the use of op amp, and the gain of the op amp is very high, that is why we can use there. So, this is the basics of precision rectifier. Why we need precision rectifier? What is the drawback of conventional rectifier? Now, different types of precision rectifier. There are two main types of precision rectifier. The first one is half wave precision rectifier, the second one is full wave precision rectifier. Like in conventional rectifiers, we had studied that rectifier is of two types, half wave, full wave. Further, full wave have been divided into two parts, one is your center tap, another one is bridge, right. There we had studied, but here in precision rectifier, half wave and full wave precision rectifier. Half wave precision rectifier is the rectifier in which we get the output only for the positive value of the input or negative value of the input. So, we get the output only for positive value of the input or negative value of the input, but in full wave precision rectifier we get the output voltage for both cases, for positive input voltage and for negative input voltage. Now, we are going to understand the circuit of half wave precision rectifier and full wave precision rectifier. So, starting with the half wave precision rectifier. In half wave precision rectifier, we can see that one op amp is used and one diode is used, and the input signal, it is applied at the non-inverting terminal of the op amp. Non-inverting terminal, that is the positive input terminal, and this diode, let us say this diode is D, it is connected in the negative feedback path of the op amp. This R is the load resistance, right. So, firstly we are going to study the working of this circuit, and we will draw the transfer characteristics of this half wave precision rectifier. The transfer characteristic, it is the graph between the input voltage Vi versus V naught. Now, see, to understand the working of this circuit, we need to understand two cases. Case 1 is when Vi is positive, when Vi is positive. Now, you can see that if Vi is positive, then the output of the op amp will be positive, because Vi input signal, it is applied at the non inverting terminal. So, we will get the positive output. So, we are getting this plus at the output, it means that this diode D will be on. If this diode D will be on, it means that the output terminal, it will be connected to the negative input terminal. So, it will become like a buffer, voltage buffer, right. So, it means that the current will flow through resistance R and we will get the output voltage. It means that for the positive input voltage, we will get the output voltage, right. So, for positive input, diode D is on. Case 2 is when Vi is negative. Now, see, when Vi is negative, then what will happen? If Vi is negative, just focus on the blue color, then in this case the output of the op amp will be negative, then this diode will be off. So, the diode D is off. If the diode D is off, you can see that if this diode D is off means open switch, then this op amp will go in the open loop configuration, because there will be no feedback now, because the output is not connected to input. Now, this op amp will be in open loop configuration. So, when Vi is negative and the diode D is off, then in this case this op amp will go into saturation. We had seen that when the op amp is in open loop configuration, it goes into saturation. Although going into saturation is not the any disadvantage, but if we deeply understand it, then we will see that it will become disadvantage. Why? The reason is that once this op amp will go into saturation, then it will take some time to get back from saturation into linear region. So, it will slow down this circuit, it will slow down this circuit. So, the speed of the circuit will become less. So, it can be a drawback also, it can be a drawback. If Vi is negative, then diode D is off and this circuit, it is in open loop configuration, it will be in saturation. Whenever the circuit will go into saturation, then it will take some time to get back from saturation into linear. So, it will slow down this circuit. That is the drawback of this half wave precision rectifier. Now, to improve the performance of this circuit, one more diode is connected, that is diode D2. Now, this circuit is improved version of half wave precision rectifier. Now, what will happen in this circuit? When Vi is positive, then since this Vi is applied at the negative input of the op amp, so positive will be here. So, you can see that we will get the negative output, because the positive is applied at the inverting terminal. So, opposite we will get at the output. So, in this case diode D1 will be off and diode D2 will be on. When diode D1 will be off, then in this case it will be open switch, it means that output voltage will be 0, right. So, for positive input the output voltage is 0, fine. Now, case 2, that is when Vi is negative. When Vi is negative, negative will appear at this terminal and the positive will come at the output of the op amp. In this case diode D1 will be on and diode D2 will be off, just focus on blue color. So, in this case since diode D1 is on, then the current will flow through this R2 resistance and we will get the output voltage. So, for negative input voltage we will get the output voltage. Again we are getting the output voltage only for the negative value of Vi. Now, the advantage of this circuit is that you can see that whether the input voltage is positive or negative, in both cases this op amp will not go into open loop configuration, it will not go into saturation region. The reason is When Vi is positive, then diode D2 is on, then this path is closed, there is a feedback. When Vi is negative, then this op amp is again in closed loop configuration with the help of this R2 resistor. So, in this case the op amp will not go into saturation. So, the speed of the circuit will be better. Now, coming to the full wave precision rectifier. In full wave precision rectifier, we get the output voltage for the positive value of the input voltage and for the negative value of the input voltage. That is why it is called full wave precision rectifier. Now, we can understand the working of this circuit again by considering the two cases. When Vi is positive, then you can see that this Vi is input signal is applied at the non inverting terminal of the A2 and the inverting terminal of A1 op amp. So, the output of the A2 op amp it will be positive and the output of the A1 op amp will be negative, because the input is applied at the negative input, fine. So, in this case diode D1 will be off and diode D2 will be on. If the diode D2 is on, then the current will flow through RL resistor and we will get the output voltage. It means that when Vi is positive, then we are getting the output voltage. Now, the second case, to understand the second case, just focus on the blue color. When Vi is negative, then what will happen? The output of the op amp A2 it will be negative and the output of the op amp A1 will be positive. In this case D1 will be on and D2 will be off. Since D1 is on, so again the current will flow through this load resistance and we will get the output voltage. So, in full wave precision rectifier we are using 2 op amps and 2 diodes, and with the help of these 2 op amps and 2 diodes we are making sure that the output voltage will be there. We will get the output voltage for the positive input voltage as well as for the negative input voltage. So, this is full wave precision rectifier. Next topic is Schmitt trigger. So, Schmitt trigger is basically a circuit which converts irregular shaped waveform into square wave or pulse. And a special point about Schmitt trigger is that it uses positive feedback. It uses positive feedback. Normally, this positive feedback is used in oscillators, right? We had seen that. Since this Schmitt trigger is using positive feedback, that is why this Schmitt trigger is also referred as regenerative comparator, because positive feedback is also called regenerative feedback and negative feedback, that is also called degenerative feedback, right. So, why it is called regenerative comparator? The word regenerative is used because it is using positive feedback. The word comparator, it is being used because it is again comparing two voltages and accordingly the output is either at plus Vset or minus Vset. Basically, the advantage of this Schmitt trigger is it improves the circuitry of zero crossing detector. Like zero crossing detector, in zero crossing detector what happens? We apply the input voltage at a particular input terminal, it may be inverting input or non-inverting input, and the another terminal is grounded. Actually, in zero crossing detector we make reference voltage V reference equal to 0. So, what happens when we apply the input signal, that is Vi versus t, this sine wave at the input of this op amp, then at every zero crossing means when this sine wave crosses, the time when this sine wave crosses this 0 point, right, that I have marked. So, whenever this sine wave crosses this 0 point, then output switches from plus Vset to minus Vset, minus Vset to plus Vset. Output will be either at plus Vset or minus Vset. It depends upon which voltage is greater at the input terminal. If the voltage at the inverting input terminal is more, then the output will be at minus Vset, otherwise it will be at plus Vset. So, whenever we use op amp in open loop configuration, the output is saturated. So, the issue is that in zero crossing detector, when the noise is added, then the input signal it may become like this. So, you can see that at the 0 point, now this input is crossing this time axis multiple times. If it is crossing multiple times, then there will be multiple switching at the output, that is undesirable. So, this zero crossing detector, it is easily affected by interference, by noise. To remove this drawback, we use this Schmitt trigger. In Schmitt trigger, now like in this circuit, we have applied the input signal at the inverting input terminal, and there are two resistors R1 and R2 which forms the voltage divider, and this R1 parallel to R2 resistor, that is R ohm, it is used to handle the offset problem, to remove the offset problem. This RL is the load resistance, plus VCC minus VE, that these are the supply voltages. Now, the voltage at the non inverting terminal, it will be either VUT or VLT. VUT is the upper threshold voltage and VLT is the lower threshold voltage. So, whenever the output voltage V naught is at plus Vset, then the voltage at the non inverting terminal, it will be VUT, and when the output voltage is at minus Vset, then the voltage at the non inverting terminal, it will be VLT, lower threshold voltage, right. So, what will be the value of upper threshold and lower threshold from this circuit? From voltage divider, VUT will be R1 upon R1 plus R2 into plus Vset, and the value of VLT, it will be R1 upon R1 plus R2 into minus Vset. Output will be either at plus Vset or minus Vset. The reason is that it is utilizing the positive feedback, although it is not in open loop configuration, but it is in positive feedback configuration. So, in positive feedback, again the output will be saturated, because the output is added to input, again it is amplified. So, obviously the output voltage will rise and it will be saturated. Now, see how this circuit works. Let us say the output is at plus Vset, then in that case the voltage at the non inverting terminal, it will be VUT, and whenever the input signal Vin, it crosses VUT, then the output will come from plus Vset to minus Vset, because whenever the input voltage Vin will be greater than VUT, then the voltage at the inverting terminal will be greater than the non inverting terminal. So, the output will come to the minus Vset. Whenever the output will come to the minus Vset, then the voltage at the non inverting terminal, it will become VLT. So, again when your Vin is more negative than VLT, then again the output will come back to plus Vset. It means that the output is going from plus Vset to minus Vset and coming back to plus Vset, minus Vset to plus Vset, depending upon the input voltage, and this input voltage is compared with VUT and VLT, and accordingly the output is switching. So, we can understand it with the help of waveform. This is the input signal sine wave, and this VUT and VLT is marked here. This voltage is upper threshold voltage VUT and this one is lower threshold voltage VLT, right. Now, you can see that whenever this input signal, it is greater than, it crosses the VUT point, VUT voltage, then in that case the output is switching from plus Vset to minus Vset, and again when input is more negative, this one input signal is more negative than VLT, then again the output is switching from minus Vset to plus Vset. But the important thing is that when the input signal is in between VUT and VLT, then there is no switching, that is the advantage. Why it is advantage? Because when the noise signal or interference is added to the input signal, then if the input signal is distorted like this, again there is a multiple crossing due to this noise and interference, then your output will not switch. But in zero crossing detector, the output, it gets switched from plus Vset to minus Vset and minus Vset to plus Vset. But in Schmitt trigger, when the noise is added and if this noise voltage is such that the input signal is in between VUT and VLT, then your output will not change. That is the advantage. The effect of noise in Schmitt trigger is very less, because whenever the input signal is in between VUT and VLT, the output will not get switched. That is a good thing. Further, we can draw the graph between input voltage and output voltage. We can see that when the input signal crosses the VUT, then the output is switching from plus Vset to minus Vset. When the input is more negative than VLT, then again the output is switching from minus Vset to plus Vset. So, this VUT minus VLT is called hysteresis voltage. This is also called, this band VUT minus VLT is also called dead band. It is called dead band because when the input signal is in between VUT and VLT, then output is not switching. That is why it is also called dead band. So, I have already mentioned this expression VUT and VLT. From here we can calculate the hysteresis voltage, that is VUT minus VLT. That is the important parameter for Schmitt trigger. So, in this class I had discussed about precision rectifier and Schmitt trigger. These are the references. Thank you.